We are now going to talk about the assumptions behind linear regressions. These assumptions need to hold if we want our inferences and our conclusion to be valid. There are four fundamental assumptions, and they are all about the population errors. The first assumption is that the errors have a mean of 0. It's called the linearity assumption. They should be probabilistically independent. This is the independence assumption. They should be normally distributed, the normality assumption, and they have equal variance. These assumptions could be remembered using the word line, L-I-N-E, for linearity, independence, normality, and equal variance. We are going to look at each of these assumptions with various plots of sample residuals. Let's look at the linearity assumption. It says that the population errors should have a mean of 0 everywhere on the x-axis. That means that there should be roughly as many points below and above the line of best fit. If you look at the graph on the right, you can see that we can get a line, and there are roughly as many points above and below the line everywhere on the graph. However, if we have this kind of data, we can see that the relationship is nonlinear. It goes down and then up again. If instead we use a line of best fit, we can see that when x is around -2, most of the errors are above the line, so they are not 0 on average. And then they are below the line around x equals 0. And then they are above the line again around x equals 2. So in that case, the linearity assumption is likely violated. Now let's look at the independence assumption. It says that knowing the value of the errors for any set of x values should provide no information about the values of the other errors. If we look at the graph on the right, we see that this is not the case. If I know that for some x the error is positive, so the point is above the blue line, we can guess that the errors on the right and on the left are also above the blue line. In the same way, if we look at x equals 4, for instance, the points are all below the blue line, so the errors are negative. This violates the independence assumption. By knowing the error for one point, I should not be able to guess what the error on the other points are. My best guess should always be 0, which is not the case here. This is commonly violated with time series data, because errors usually display trend over time. This is called autocorrelation. It means that each error is correlated with the error just before it. We can actually check if this independence assumption is violated with a statistic called the Durbin-Watson statistic. The third assumption is the normality assumption. It says that the distribution of the errors should be normal or Gaussian. Note that this is not the same as saying that y follows a normal distribution. Here we are just talking about the errors. We can check this assumption by plotting the sample residuals. If we put them on a histogram, we could look that the histogram is roughly bell-shaped. We can also use another tool for that called the QQ plot. Here we have two histograms of the residuals. We can see that on the left it's roughly bell-shaped, around 0. So it passes the assumption that the errors are normally distributed. We cannot reject this hypothesis. However, on the right, it doesn't look like it's bell-shaped, so we would reject the assumption that the errors are normally distributed. Finally, the last assumption is that we have an equal error variance. It says that the variance of the errors should be the same no matter what the value of x is. If we look at the plot on the right, we can see that we can have the distribution of the points and that they are roughly equally distributed in the left, middle, and right section. So the variance of the errors remain roughly constant. However, if we change this graph to that other graph, we can see that the errors have a small variance on the left, then it increases when we go to the middle, and it is a large variance when we look at the right. When the variance of the errors is constant across all values of x, we say that the errors are homoscedastic. So we have homoscedasticity. However, if the variance of E depends on the value of x, then we have heteroscedastic error. So we have heteroscedasticity. We can always look at the variance of the errors by just plotting the residual on a graph and see if the variance of the residual is roughly constant or not. If we have residual with changing variance, we can guess that the errors also have changing variance, and likely the equal variance assumption is violated.